Okay, we're good. All right, let me. What's the stuff going on here? Switch over back here. All right, everybody. Hopefully you can hear me good here. It looks like I'm good on YouTube and LinkedIn. LinkedIn's a little funny with the live streaming. I know last time it didn't work exactly correctly, but I think we're going good on both. And I've got the chat up for both right here. So I'll shrink down in just a second. But what I wanted to start off today with is, make sure I switch over here. There we go. I got two drawings that I kind of just found laying around. So I thought I'd get started just talking about this and, talking about drafting as well as what I would do GD&T wise to these two detail drawings. It is, all right, thank you. It is an assembly. It's very simple, but an assembly nonetheless. I know that's a common thing, and I understand, if you know GD&T pretty well, you're like, okay, well, I'm pretty sick of just like applying GD&T to like one thing. Like it's not super helpful because it's supposed to be like an assembly wide thing to make sure things fit together at the assembly level, or parts fit together at the assembly level. It's just really difficult to show that without getting like, pages and pages and pages of, drawings and, calculations or whatever. It just gets very voluminous very quickly. But I'll try with these two little drawings here. And then I had a question about angularity, so I'll just talk about angularity real quick. Something you don't see all the time, and I think it's misused a good amount. And then we'll see where it goes from there. So feel free, if you have questions, put them in the chat. I'd be happy to answer them if I can. And if you have any of these drawings, feel free to send me, something you're working on in college, maybe stuff you have sitting on your computer that isn't, covered by a NDA or anything. I might be able to use them for, this purpose here. Okay. So the way this little guy works, it's just kind of a, what do you call those things? Fidget spinner. It's designed for machining students to make this little slot, right? This little T-slot thing. And then they're going to put this kind of bolt in there. So the head of the bolt is a diameter of 1.1 3/8 basically. And then this little slot is 1.4. So you have like a little bit of wiggle room right there for the head. So let me just draw this real quick. So it would be something like this, right? Where this is the threaded member. Right, a little hex head bolt. And then there's, on the other side, a nut of some kind, which we don't have a drawing of. But the idea, and I know it seems kind of silly, is that this bolt just traverses up and down, right? You can tighten the nut and move the bolt, to the top or to the bottom, or just let it slide around. Really just a little machining project. And then something, obviously we can talk about here. So that's the function. You can see it's already got clearance for that hex head built in. Or I'm sorry, is it a hex head? It's not a hex head, it's a round head. So that clearance is already built in. The biggest thing we want to think about here, design wise, is what do we want to locate essentially left and right, right? We have two interfaces here. So what I mean by that is that we've got our bolt, right, and the head of the bolt. Yeah, it's for clamping, but it's kind of like a useless clamping. Maybe it's taken from something that's useful, but as far as I know, this thing has no practical function. Okay, so what I'm talking about is there's a gap here and there's a gap here, right? So we'll call that 1 and 2. And you got to decide design-wise which one is going to limit the left and the right movement. It could be either one. I wouldn't say there's necessarily a right or wrong answer here. It's probably going to be the smaller one, but one of them needs to be, limiting the other. And what that allows you to do is have one of them have a big, large tolerance and the other a smaller tolerance, instead of making them both have like a really small tolerance. You don't necessarily want to do that, right? So you think you move this left and right, it's either going to hit right here or it's going to hit up here first. So you want to know which one that is so you can apply the appropriate tolerancing scheme to this. The next thing, right, our bolt, right, the datum reference frames are kind of going to develop themselves. So the bolt sits down on here. I mean, we really don't have a lot of choices here. So, I guess it's not really against the rules, but I don't like fractional. I want to say it's against the rules in some obscure ASME standard. I like decimals there, except for pipe threads. Pipe threads is still cool to use fractions, and you can feel free to disagree with me if you want, but and I can't remember if it's just like a drafting look-alike thing or if it's really a problem. In any case, we're going to call this 0.75010 UNC2A. I'm sorry for all our metric friends out there. Eventually, I promise, I'll learn some metric threads and start throwing them in here and stop using customary units all the time. So check it. We would have this. It would have, right, a leader with a little bent. And let me draw it over here. I know I'm taking up a lot of time talking about this thread. UNC2A. Right, so I'd make that our primary datum. So it's weird. In this case, what's really going to orient this screw in space isn't the axis of the thread, which is uncommon. Normally, you thread something in, and that's what's going to locate it in space. So, if we have a threaded hole and we thread a fastener in there, right, it's going to be the shaft of the fastener, the axis of that locates this in space, not the head of the fastener, right? That is only going to get one point of contact because it already is being located by the thread. Not in our case here. So when this thread sits in here, there's going to be clearance probably here. And in any case, it's not going to set the orientation in space. What's going to set the orientation in space is this flat. So hopefully nobody screenshots me here, but I would, in this case, probably say I'd probably make this datum A. And I know say screenshot me like I'm an athlete or something, but you know what I mean. It's a point of contention. Normally you wouldn't see this. You almost always would see the thread as the primary datum in this case, but I'm going to say it's not. So what we have to do here is apply some kind of tolerance to the axis of the thread now. So I go ahead and say, hey, that's perpendicular to datum A. Just because there's one of it, it can be perpendicular. It doesn't have to be a position or anything. And we come in here. I know I'm almost in the way. Make that datum B. Another thing that kind of bugs me about this drawing, we need a nice center line. So I know if you're like a checker or whatever, you've probably been screaming at your screen the whole time here. So we got a nice center line there. That cleans it up. Okay, datums A and B. What we could do to make this a little bit easier is to call this out at major diameter, and it just makes it a little bit easier to inspect. And in this case, it's totally fine because we're not necessarily threading it into something that's going to orient it in space. It's just going to thread into a bolt and provide that clamping force. Oh geez, I don't know what that comment says. Okay. All right, so we'll stick with this part for another minute. Basically, everything else should be things we've talked about, right? So we've got a outside diameter here. Oh, here we go. I should probably just look for where it's already been dimensioned. So we've got an outside diameter here. One little bone to pick with this, it's not one diameter, it's two diameters, right? Because we've got this little gap right here, this little radius or whatever. So we've got a diameter, a diameter. We can take care of that in a couple different ways, right? We could say 2 times and then put a position on it, or we could use our handy new continuous feature symbol, which is kind of what it's for, situations like this. Just for fun, I'll just use the continuous feature symbol. And we'd apply a position to this, right? I'm just going to go 0 MMC to A and B. In this case, it has to be position. It can't be perpendicularity because we're locating one axis to another axis. So essentially A is going to orient it, and then B we're trying to, we're setting up our cylindrical tolerance zone that's coaxial with datum B here, right? This axis from this thread. And otherwise it works the same, okay? For this little radius thing here, I'd probably call that out as profile. So we'd go ahead and make these dimensions basic, which I think cleans things up a little bit. And then I'd just point in there with a profile. All right, come out here. Profile of something to A and B. And we could control that feature. Here's a kind of weird one. Right, we've got this diameter 0.625. This is a thread relief, basically. It's to allow the tool a little bit of room to kind of run free so the machinist can pick it up before it hits something. There's other uses for it, too. It's a common thing on machine turn parts. It's kind of a pain to measure this for position. It's almost something you would want a visual check on to just see, okay, it's not way out of whack. Normally, it's not going to have a huge effect on anything. This is a result of the machining process of making the thread. So, there can always be weird stuff that happens, but I would say usually it's uncommon. So what I'm getting at is this is something you could potentially just say, hey, it's a plus or minus. We're just not going to bother with the geometric tolerance here because nobody's going to check it anyway. They're just going to put calipers on it and make sure it's not too small. So you might see that out there. I've put that on drawings before, and it could be fine. If you want to be cautious, you just put a position on it just like any other, just like this position we talked about up here. Okay. Next up, let's look at this little feature. So let me get a different color. Here we go. So I'm going to look at this little cutout, and it looks like it's for a screwdriver, but I don't think it's properly sized. If you go deep in the machinery's handbook, somewhere there's like, the sizes you need for slotted screws. So if you need a number 2, slotted head, it'll tell you exactly the shape of the slot you need, right? I don't think they did this. It seems like this should be like that big. I don't know. Okay, check it out. What would we do there? I would probably lean on just saying, hey, let's make this profile, right? We'll go from here to here, and we'll call out a nice profile of something to A and B, and we'll say G to H. And then in my calculations, right, it would have a basic dimension. So let's say it's 0.10. I don't know what it is over here. 0.125. Whatever. 0.125. Whatever it says over here. Make that basic. What I would do is just figure out what the minimum is. So if my tolerance is 0.02, I've got 10 here, 10 here. So I'm essentially taking 0.125 minus 10 and 10, so 20. 0.120, so I've got 0.105 is the minimum size. So as long as I know my screwdriver will fit that, I'm good to go, right? The maximum size of my screwdriver tip is less than 0.125, 0.105. And I know, again, sorry for my friends out there using metric and SI. I know it's got to be like a headache, constantly kind of not converting, but it's just numbers you're not used to hearing. So this would be a relatively large tolerance machining wise in customary units. Okay. That's how to handle that. Why do I say that? Why would I do it that way? Well, the alternative is to use position. So let's discuss that real quick. This drawing really is a treasure trove of stuff to talk about, right? I thought I'd be over with this in 5 minutes or something. Oh, here, we want to add a center mark up here. Sure. Again, some people have been screaming at their screen. And you know what? While we're talking about drafting stuff, you want to turn off your tangent edges. If you want to know why it looks like you have ants all over the part here, like ants marching around, it's because the computer is trying to show all of the little radii. It's trying to show this on this view, and it's trying to show all of these features on this inside. It makes it look like you have ants on your drawing. In this case, it's not the end of the world. I just think it looks bad, crowds up your drawing. So in SolidWorks, you would right click on that view and go down. There's something that says tangent edges off. There's like 3 options, but you want to turn that off. Where it sucks with SolidWorks, and I'm sure they're 100% people are better than me at SolidWorks, right? I don't claim to be an expert or anything. But generally with CAD, if you have a view and you have a bunch of hidden lines, it's not easy to turn some on and some off, right? You either have them all on or all off. Maybe there's a way to choose what gets shown and what doesn't. For me, I just probably have to go in there and draw it manually if I had to show a hidden line and hide everything else. Okay. Oh, we were talking about position and this slotted feature. Yeah, right. Those tangent lines, they just, I don't know, they just crowd stuff up. And every CAD program does it a little bit different. So, and what a CAD program should do is if you're going to use hidden lines on views on one sheet or whatever, they should be in every single view. That's not how it works, because typically CAD programs are default to not having tangent line or not having hidden lines. So you got to go in there and turn them on, right? So you might have one view with them, and then a view projected from it doesn't have them, and then chaos ensues, right? Here's the other thing about hidden lines. You don't really need them because you shouldn't dimension to them. They're just there to help you understand what's going on, but if you need that, you should probably just have a section view to show you like what's really going on, not a hidden line kind of just hinting at what's going on. Because again, you can't put a dimension on it. So it's kind of like hearsay. It's like there might be a feature in here, but don't worry about it. It's on some other view that you can actually see. So why put it on the view where you can't actually dimension it? Okay. So what we would do here is have instead of, so we've got this 0.125, let me draw that correctly. We'd want to do 0.125 plus or minus something, right, in order to use position. That's one of the requirements for a position tolerance. We have to have a feature of size. So I'd come in here. Wait, man, I never give myself enough room. Let's flip the script here. I'm going to draw it the other way. There we go. There we go. We've affected a lot of extra room here. 0.125 plus or minus 5. We're going to slap a position on there. Let's say 0 at MMC to A and B. Why 0 at MMC? It just makes it easier to calculate in my head. So I'm going to look for the MMC of this, which is going to be 1.120. That's the virtual condition, right? That's the size of the largest, the smallest, whatever. It's how you you size up the screwdriver tip. It doesn't have to be 0 at MMC, but that's how we would do that. Now, why do I not recommend this option? Well, now we have part of it that's not dimensioned, right? So we've got this little spot down here, which probably doesn't matter, right? We could say, whatever, we'll just put a plus or minus dimension on it. And you could do that, but say your checker walks by and is like, hey, we're not doing plus or minus dimensions to locate surfaces. Haven't you heard about 2018? ASME Y145-2018. Can't do that anymore. Well, now you're going to have to put a basic dimension on it, and you're going to have to come in here with like a profile anyway, right? Right. This whole position thing was to like not use profile. Well, now you have two geometric and two feature control frames, essentially controlling the same feature. What's the advantage with position? I guess you could say it's more functional. It does allow you to use the MMC. So there could be a situation, I don't know, with a screw tip, right? If it gets too big, the screwdriver don't work good. But there could be a situation where it's okay if it's larger. In that case, position works out here. I'm just trying to illustrate here that it could lead to additional feature control frames, which could lead to shops quoting you extra just to interpret those feature control frames. Okay, I think that's, real quick. These locational dimensions, probably not that one. We would just use profile, right? No big deal to locate those surfaces, just like I was complaining about right here. It's easier on these surfaces though, because they're external. So, not too big of a deal there. I think I made a video about that at one point. I had like a threaded thing. I flipped it over in a V-block and measured it for profile. It's really not a big deal. Okay, I think that's all all we can extract from that one. Wow, that put us at 25 minutes already. Okay, I don't think this one will. Well, actually, I have no idea how long this will take. All right, let's see what we have going on here. This, I can already sense what's happening here. This would make a sweet datum A, right? When I say datum A, I mean primary datum. That doesn't have to be A, but what I'm saying is when we come up with our datum reference frame, A is gonna come up first, okay? Isn't that covered with a slot profile tall? Huh. Yeah, let me check questions real quick. Cool. Yeah, Brian, I'm not sure what you mean by covered by the slot profile tolerance. Yeah, let me know if you want me to go back to that one. Actually, let me check this real quick. Hopefully, I could be heard on LinkedIn as well. I know last time, like, it didn't stream to LinkedIn or something. And then I checked it, and there's like a frame rate. Oh, okay, I can see myself. That's cool. Yeah, it's like a frame rate problem, but they don't tell you about that before you start streaming. There's like, oh, by the way, your stream don't work. So let me check that. Okay. Oh, man, I accidentally liked my own stream. That's lame. Okay. So datum A makes sense here, right? It's where, our mating part, the datum A is that super sweet when our datums literally match up like that. The problem, and I've seen this a bunch before, if we make that our datum A, it becomes more difficult to deal with inspection wise. Even with the CMM, we could run into some problems. So what do I mean by that? Well, if we're going to measure this on a CMM, we're going to come and probe it probably from the top, right? So let me draw little probes here. Depending on the size of the part, I think we'd be okay here because we could get point here, and essentially probe, right? A good few points. I think that'd be enough. What could happen though is if this overhang, so if this overhangs like all the way, right now I can't get a normal probe in there. Now they make all kinds of like funny probes. You could be like, oh well, I'll just get my probe that has like this custom probe that like goes in like sideways and does it. But then you got to buy that, right? And then you got to spend a bunch of time qualifying it, and then you got to like make sure your qualification's right, and especially preferably you want to be able to just get it with a regular probe. Okay. If you got if you're CMM expert, feel free to chime in if you disagree with me. This is kind of how I see things. All right, so that makes it an inconvenient datum for a CMM. Also, not super easy to measure with on a surface plate, like this, like a granite plate with like metal stuff, right? So, say we did have this overhang, right? Even if this is the functional feature, we would probably want to make something else datum A, right? Because it's going to be the thing we could put the part on. What do I mean put the part on? So I know it's not the same thing, but say we make this surface right here, right, this inside surface, datum A, it's doable. But it's not as sweet as if this surface was datum A. If that surface is datum A, we just put it on the plate and we're cooking, right? We could also, right, just stick it right on our little block here and, measure from the other side, right? It's pretty sweet too. It's not the end of the world because this is open, right? I could do something like this to simulate it. Not the end of the world, but slightly more difficult. Okay. There's always going to be a give or take with the datum selection stuff. My thing and what I kind of want to get across with these streams, the videos in general, is just to be able to defend yourself, right? Just to be able to talk about it and walk through your process. Everybody might not agree with you, but this is my process. And again, everybody might not agree with me, but you want to be able to vocalize kind of why. Without just pulling up pictures from the Y14.5 standard. I mean, that's fine, but if you can kind of talk about why, I found that helpful. Okay, check it out. So after all of that, what decision am I going to make here? I'm going to stick with this as our primary datum. I can get to it with a CMM probe. I can live with it, right? It's a very functional feature. Secondary datum, we're probably going to need 3 in this case. So this is going to take away 3 degrees of freedom. Now, this is where, okay, what would be ideal, right? It'd probably be like some version of this feature, right? Like the center plane of this slot would be like super ideal because that's essentially, you got the axis of this bolt kind of riding along here. I would probably push back on that because it's going to be difficult to capture that. And I don't think functionally it really matters all that much for what this little thing does. So what I would say, I would actually go with the author. The drawing here, they give us a little telltale, right? They're dimensioning this from this side. I'll just make this side datum B. right? And then datum C, I would just come over here. Now I could get some disagreements with this because now we've got like an asymmetrical thing going on. But I think for the purposes of the functionality of this design, I think it'll be okay, and it'll be much, much easier to deal with. This is the kind of problem you run into in CMM metrology, is like they might put one datum reference frame on there, but all the dimensions come from a different datum reference frame, right? If they're basic dimensions, it means the same thing. Shouldn't matter, but you never know what you're going to get. Again, this should have a center marks at the very least. I'd probably put a center line here and probably have a center line going down the middle of the part. Okay, I got a question real quick. Which geometric tolerances can use the MMC modifier? The answer is anything controlling. Okay, so let me write it. So position can use MMC perpendicularity, right? Angularity, parallelism. I won't write out those full feature control frames. Flatness, if it's applied to a derived median line. Straightness, if it's applied to a derived median line. Yeah, that's it. So how do I know, right? You don't have to memorize this, right? This is not, it has to be a feature of size, right? So instead of looking at the feature, at the symbol, I would look at the feature itself. Is it a feature of size? And almost always a feature of size is either a width or a diameter. If that's the feature, you're going to be controlling it, and you're controlling the position, right? We can have MMC. Where it gets a little squirrely is you might have, right, a cylinder that has a profile applied to it, right? So the cylinder is a feature of size. Here's the weird thing. The profile applies to the surface, right? It's in the name, profile of the surface. So even though the feature is a feature of size, the geometric tolerance applies to the surface only. That's why there's never a diameter symbol in front of a profile, in front of the tolerance in a profile. Ditto goes for runout, right? Runout will never have the MMC symbol because runout applies to the surface of the part. Again, you don't ever see a diameter symbol with runout, right? Because the tolerance zone isn't a cylinder inside of the part. Always applied to a feature size, yes. Okay. In your previous example, the slot width and the head of the screw was a feature of size with the tolerance between G and H. How do you handle profile with the feature of size instead of a basic dimension? Maybe I miss. So if I did this, I'll correct it. Let me switch back over. Oh, oh, so that's not the drawing anyway. Oh, did that erase it? Okay, we're good. Okay, cool. Okay. So if we have like a slot feature, and I'm gonna go profile. I gotta remember how to draw here. We're gonna have to have basic dimensions here and here, right? There's no way around it. Especially in the 2018 revision of the standard. Now, yeah, there's no way around it here if we want to control the location. There are some situations where you could use profile kind of like parallelism. In this case, it wouldn't work. because we're controlling essentially a feature of size. I'm not sure if I would want to encourage thinking about it that way, but it's a collection of three surfaces. This is a feature of size. It gets, if you're ever really bored, check out like the GD&T forums. This kind of stuff people have go wild over. I mean, it's amazing how detailed the posts get, just going back and forth on the real subtleties of the ASME and ISO standards. If you're curious, there's a website called I think it's got a hyphen, ingtips.com, and they have GD&T forum. It's like called like drafting in GD&T or something. I'm a member. I post not that often, but I do read a good amount, and they've got some pretty detailed posts in there. You can search some stuff and like, wow, that's you see what I mean if you ever go check it out. Okay. Hopefully I got that one answered pretty good. So we've got our datum reference frame here. Again, with these tangent lines, woof. I mean, just ants marching all over the place. Yeah, I would totally get rid of all of that. Or if you really needed it, right, you could section this, right? So I just put in some lines. If I section it, now they can all become, right, nice visible lines with section lines, right? That's the way I would have gone here. Okay. Now, I think everything on this drawing is pretty straightforward except this slot feature. We could control most things on the drawing, a profile or a position. The slot is a little weird. Let me draw this a little bit bigger over here. Okay. So we got a slot feature. I see this all of the time. And someday I'm going to make a whole video about just slots. Okay. So say we're controlling this. So we'd have 2 times R here. We'd have so if you want to know what I'm looking at here, here's the 3 acceptable ways to measure a slot. Just like I'm sure most of you, I don't remember everything all the time, but this is 1994. I don't think it's changed at all. So I'm going to use this one. 2 times R, the distance between center points, and the width here. So if we're using position, right, these are all going to be real numbers, or not real numbers, what am I saying? Dimensions with a tolerance, and not basic. Now, I would say, in my opinion, I think this is wrong, right? Because it's regardless of feature size. Now, what does that mean for us? Well, normally if we apply regardless of feature size to like a hole, it just means the axis of that hole is, what we're measuring. I think I made a video about this one time, surface versus axis method. Don't worry about all that for now. But basically when you measure a hole, you get an axis, you see if it's in a cylindrical tolerance zone. If you're measuring a slot, right? Or not this kind of slot, like a groove, right? You find the center plane and see if it's within 2 planes. With this, the question is, what is the feature and what is the tolerance zone, right? I can tell you right now, there's no support in Y14.5 for like a small slot shaped tolerance zone, right? That's not like a thing. And the other thing is like, what's the derived element here? Like, is it an axis in the middle of the slot? And if so, where does it come from, right? When we're measuring, say we've got a hole, right? The definition for this is pretty straightforward. of the unrelated actual mating envelope. It's the largest similar feature you can fit in there. So you imagine the largest gauge pin you can fit in there. For an external cylinder, it's the smallest cylinder that collapses on it. Now you could say, okay, well, all you got to do is get a slot-shaped unrelated actual mating envelope and expand it, right, simultaneously in all directions. I guess. I don't know. I know you couldn't physically do that. Maybe with a CMM, and I've seen CMMs do it weird ways too. I'm pretty sure Zeiss just gets an axis from here, and I'm sure somebody can correct me on that. What I'm getting at is it's tough. It's not clear what's going on. You can make different arguments. I can tell you this. Y14.5, Y14.51, the math standard, nor the data measurement reporting standard show this ever as an acceptable way to dimension a slot. There's no support for how to interpret it mathematically or how to report the data. Okay, so if you see this on a drawing, I just don't think there's an accepted way to interpret it. Okay, if on the other hand we check and you know, sometimes I give people a hard time for just going by what the pictures look like in Y14.5. That's not a bad way to go, right? Because people are going to open the standard and be like, oh, okay, looks just like what you have on the drawing. Perfect. Case closed, right? So if you don't have to go out and make it look different, you know, don't. This is the figure, right? This is what it would look like. It'd be a position with MMC. Now, what does that do? It just means you're going to set essentially this same slot shaped thing at the MMC size of whatever this is, right? So you'd find this dimension and then this dimension, and then the ends would just be radii, just fixed tangent radii, and you just make sure the slot doesn't violate that zone, right? So that's called the surface method, and that works fine. If it's just one position, applies all the way around. It can be two, so you might see instead of this, there might be one position here, right, to A, B, and C, blah, blah, and then one down here. And this is clever, and this is what we would use in our example. This essentially, right, see, this has more tolerance. This is going to shrink down the size of our surface, right, of our boundary. So the slot could be, you know, smaller, right? It just gives it more tolerance. However, this one, you know, it can vary less. So normally that's what you'd want with a slot, right? If this gets too, this dimension is too small, bolt or whatever won't fit in there, won't do its job. But the overall length often doesn't matter because it's like an adjustable type thing. In our case, it doesn't matter either, right? If this comes out, let me get a better color. If this comes out a little bit small, right, our fidget spinner will still do what it's supposed to. It won't be, I don't know, as exciting, I suppose. Yeah, that would be acceptable. But if it came out, say, like this, right, long and skinny, the bolt might not fit in there and it wouldn't work at all, right? So we can kind of modulate that slot tolerance. The other way to do it, and I don't know, I would say I probably recommend this for most cases, is just slap a profile on it. The disadvantage with the profile is that you're controlling both sides of the tolerance, whereas at the position you're really just worried about the inside, or the inside of the tolerance. What do I mean by that? I mean, with position, like, it could come out like that and be cool, like, who cares? I don't want to say who cares, but with profile, you're going to have this fixed tolerance zone all the way around the part that never varies, right? It's always this number. With position, you get different number going on there. All right. Okay. Cool. Let me check something over here real quick. Oh, wow. We're already at about 50 minutes. So if you have any questions, please just put them in the chat. And I can try to get to them. Just checking to make sure this is kind of working everywhere else. Huh. Wow, that's so weird. Okay. All right, guys. So I know I said earlier I'd get to angularity. I'm trying to see. Do I have time? I guess I have time. I said I would cover it. So I think we're good on this drawing. I think we spent so much time on the other one. We're basically good here. Let me switch over. That's going to be if I define the surface that position. Let me switch here. Let me check this real quick. Oh wow, 20. Okay. So angularity. Angularity is a funny one. It's one of the orientation tolerances, right? So it's in the same family as our friends perpendicularity and parallelism. Angularity is supposed to be used for angles other than 90 degrees or 0 degrees. So other than perpendicular or parallel. So if you have a 30-degree angle, you can control it with angularity, whereas you could not with position or parallelism. So in a typical case, right, let's say we have a little block right here. We can control this surface with angularity, right, to a datum reference frame. Now, with angularity, probably the biggest thing is that we have to specify the angle. I know it's a terrible job of showing an angle, but essentially we got to specify that. Well, it brings us to the question of, wait, where do the basic angles for everything else come from? So what I mean is, say I slap a perpendicularity on here, right, perpendicular to A, what's happening is that your basic angle is there. It's implied. And in fact, you know, all angles are implied all the time. So if I took this corner right here, right, that we don't have any geometric control on right now, it's 90 degrees, but it's going to be plus or minus whatever your general tidal block tolerances are. Okay. Does that get checked? Probably not that often. Probably only when something doesn't work, right? That kind of thing would get checked, but it's there, whether you like it or not. Now, what happens with orientation tolerances is that 90-degree angle is hanging out there, but it becomes basic. Now, this plus or minus 1 degree does not apply to this. This orientation tolerance takes over. Normally, that's going to be more tolerance, right? So if we're doing plus or minus 1 degree from this surface to this surface, I mean, I guess it depends how big the part is, but that's not much, right? It's going to be a wedge shaped tolerance zone. So we're going to have more tolerance up here than we have down here, right? Probably not super functional. Whereas with our orientation tolerance, right, we've just got two parallel planes set to our datum reference frame. Okay, so that brings us back to our angularity. I think the way to think about angularity is it's just, you know, parallelism at an angle. So what I mean is, do I have... With angularity, say I have this little block with this angle, right? I'm going to put it on the plate and rotate it up, right, by use of a sine bar, which I don't have handy, and check it just like parallelism, right? So it's not the only way to do it, but that's the best way that I can think of to think about it. You set a sine bar to 30 degrees, and now this surface is nominally parallel to the granite plate, so we can run an indicator and test it just like parallelism. Now, what angularity can't do is control the location of the surface. So the number one thing I see is people putting a plus or minus dimension for the angle, right? That doesn't make sense in this case. The other one is using basic dimensions to locate the surface. It's got to be plus or minus dimensions, right? If it's basic, then this is an incomplete drawing requirement. What you would really want is profile, which works just fine. But if you're going to use angularity, just keep in mind, you're only controlling the orientation of that surface, not the location and space. Let me check this for assuring sheet metal part. So I'm not sure. Oh, here's the chat. Yeah, Santiago, try to email that to me. You know, just write it up however you can, and I'll try to answer that in a separate thing or another live stream or something. That's going to be a little bit too much for me to imagine here and draw on the board. But I appreciate you putting it in there, and yeah, just try to shoot me a direct message or an email, and I can get to that. It's a cool topic, but it's going to be a little bit too much for me. Plus, yeah, we're right at 55 minutes. So I'm going to end in just a minute here. If there's any... Okay, cool. Again, thank you for the questions. So yeah, if there's any last minute questions, if there's other stuff, you know, DM me on LinkedIn, send me an email. You can find it through my website. Real quick. I do have... Right, website, it's just my name. Type in Dean Odell, you find me. There's a place where you can contact me, right? There's other ways to find my email address. Not like a secret or anything, but this is one way to do it. You can add me on LinkedIn. Feel free to do that. Send me a direct message there. Yeah. So that's all I had. I don't want to drag this out too long. I'm going to check the chat real quick. Okay, a little bit of LinkedIn chat. Okay, guys. Well, thanks for tuning in again. I will see you next week. So later.